For a lot of us, the periodic table is just this thing we remember from a dusty classroom wall, a really confusing chart of letters and numbers. But what if I told you it's not a chart at all? It's a map, a chemical map of the entire universe, where every single element has its perfect place for a very, very specific reason. And today, we're going to decode that map.
And the first mystery we have to solve is this one. Why does it have that weird, jagged shape? I promise you, it's not random. That shape is actually a code, a visual key to understanding how all matter is built. And by the end of this, you'll know exactly how to read it.
Okay, let's dive right in. At its very heart, the table is a map of matter. And just like any good map, it has a simple, organizing principle that puts everything in its right place.
So, the most fundamental rule is the atomic number. That's just the number of protons in an atom's core. We start at the top left with hydrogen, which is number 1. Then you move across the row to helium, number 2. Then you drop down to the next row with lithium, number 3, and you just keep going, filling the map one element at a time. See? It's a perfectly logical progression.
Okay, so the numbers give us the basic order, but the real magic, the part where the patterns really start to pop, comes from the geography of the map, its rows and its columns.
The horizontal rows are called periods, and they tell you how many energy shells an atom's electrons are filling up. But the vertical columns, those are called groups, and that's where it gets really interesting. You should think of them as chemical families, where every single element in the same column shares key properties and behaves in a strikingly similar way.
For instance, everything in Group 1, the alkali metals, they're all super reactive. They're just desperate to give away an electron. But then you look at Group 18, the noble gases, and they're the total opposite, stable, aloof, and they do not want to react. Their spot in that column basically tells you their entire personality. It's a family resemblance, written right there in the language of chemistry. But what actually causes that resemblance?
Well, that brings us right back to our central mystery, that strange shape. And the answer isn't in the protons, it's in the world of the electrons that are swirling all around them. The shape of the table, it's the hidden architecture of the electron world.
You see, the table's unique layout wasn't some design choice. It is a direct visual map of how electrons fill up different energy levels, or orbitals, around the nucleus. You can think of these orbitals as different neighborhoods where electrons are most likely to hang out.
And this is how it all works. These little neighborhoods have different shapes. The simplest one is just a sphere. That's the S block you see on the left. Then you get a more complex dumbbell shape. That's the P block over on the right. And the even more intricate D and F blocks are smacked in the middle and down at the bottom. The table's weird shape is just following the strict order in which electrons fill these neighborhoods up, one by one. It's a perfect blueprint of an atom's electron address.
Now, to truly read our map and start predicting how things behave, we have to understand two invisible forces that define every single atom. It's a constant push and pull happening inside.
It is a constant battle. On one side, you have the positive protons in the nucleus, and they're pulling all the negative electrons inward. But at the same time, all those electrons are negatively charged, so they repel each other, pushing outward. This constant tug-of-war is what determines pretty much all of an element's properties.
Okay, so this repulsion creates something really cool called the shielding effect. Imagine you're at a huge rock concert, and you're trying to see the band on stage. That's the nucleus. But the big crowd of people right in front of you, those are the inner electrons. They're blocking your view. In the exact same way, those inner electrons shield the outer electrons from feeling the full attractive pull of the nucleus.
So the whole thing boils down to this one crucial idea: effective nuclear charge. It's not the total charge of the nucleus, but the charge that an outer electron actually feels after you account for all that shielding from the inner electrons. This one value, this is the key to unlocking pretty much all the periodic trends. All right, now that we have the keys, we understand the map's layout, and we get the idea of effective nuclear charge, we can finally use them. We can read the map and predict exactly how these elements are going to behave.
First up, let's just talk about size. The atomic radius is simply a measure of how big an atom is. So how does that size change as we move around our map?
Well, it follows this beautifully logical pattern. As you go down a group, you're adding whole new layers of electrons, new shells, so of course the atoms get bigger. But, and here's the part that might seem a little weird, as you move from left to right across a period, the atoms actually get smaller.
Why? Because you're adding more protons to the nucleus, which increases that effective nuclear charge and pulls all the electron shells in tighter and tighter. Let's move on to ionization energy. You can think of this as a measure of how possessive an atom is. It's the amount of energy you need to steal its outermost electron. Is it easy to just snatch that electron, or does the atom put up a real fight?
And here's the really cool part. Ionization energy is basically the inverse of the atomic radius. A big atom, where that outer electron is super far from the nucleus and really well shielded, has a low ionization energy. It lets go of its electron pretty easily, which makes it highly reactive. But a small atom, with its outer electron held in a death grip by a strong effective nuclear charge, has a really high ionization energy. It puts up a huge fight to keep its electron.
And that brings us to our final big trend, electronegativity. If ionization energy is all about keeping your own electrons, electronegativity is about stealing someone else's. It's the measure of how strongly an atom pulls on electrons from other atoms when it's forming a bond.
And the trend here is just as clear. The desire to pull in electrons gets stronger and stronger as you move up and to the right on the table. This makes fluorine, sitting up there in the top right, the most electronegative element of all. It is the ultimate electron thief. And francium, way down in the bottom left, is the least electronegative. It's way more likely to just give an electron away than to take one.
So let's just step back for a second. We've decoded the layout, we understand the internal forces, and we've got the major trends down. We've cracked the code of our chemical map. So, what's the big takeaway here?
The real power of the periodic table isn't just that it organizes stuff. It's the profound elegance of the whole thing. It's how the atomic number, the electron setup, the atomic size, and all the chemical reactivity, how it all interlocks so perfectly. It's this beautiful system where everything just fits.
And because everything fits so perfectly, it becomes probably the most powerful predictive tool in all of science. By just knowing an element's position on this map, we can predict its properties and its behavior with incredible accuracy, even if we've never seen it before. It is the absolute foundation of modern chemistry.
And this really brings us to a final thought. The periodic table shows us that there's this deep, hidden logic in the very fabric of the universe. It kind of makes you wonder, right? What other profound patterns are out there, hiding in plain sight, just waiting for us to find the key and decode their secrets?